grade 10s. This is physical science. My name is Gillian. Today we're going to be looking at the basics of bonding. So we have covered a little bit in the previous lesson. So now we need to continue with looking at ionic bonding. What is it going to look like with Lewis? We're going to look at covalent bonding. What is it going to look like with Lewis? And then we're going to have a look at some problems. So let's look at the screen and see what we've already covered. So we've already discussed quite a bit of the periodic table, and I hope you've realized that being able to use the periodic table is really an advantage. The only way you can get to know it is by practicing with it. Then we had a look at atomic structure, and we spoke about the valence electrons and how they are involved in bonding. They're really important. So we need to know how many of those electrons are going to be shared or given away or taken. Then types of bonding, we have got covalent bonding, ionic bonding, and metallic bonding. So we are going to do a quick review of ionic bonding. We're going to have a look at the covalent bonding, and we're going to get to metallic bonding. Representation, we've already started with that. We have already discussed how Lewis works. The Lewis representation, we've had a look a little bit at the notation, which is the SP notation. 1 is 2, 2 is 2, 2p. Let's call that 3. Okay, so that's the SP notation. We've already had a look at that. And there's another one that we might have time to get to, and that's the Aufbau diagram. Okay, so we might have time to get to that. We'll see. Right, let's head in then to do a quick review of ionic bonding. So ionic bonding is between a metal and a non-metal. I have here sodium. You can see that there are 3 electrons, 1, 2, 3. We really should count the protons. There are 3 protons there. That tells us a neutral atom has got 3 electrons. And on the periodic table, we'll see a number 3, which is the atomic number. And that tells us how many protons are in the center, in the nucleus of the atom that we're dealing with, right? That's the atomic number. I have chlorine. There are 17 here. This is just a bit much to count, so I counted the electrons. And you'll notice that these electrons are the arrows that represent the electrons. One spins one way, one spins the other, and that's why they are the opposite way around. That's the Aufbau diagram. So if we have an Aufbau diagram, we draw in little squares like this, and we represent the different layers of the different orbitals and their energy, different energy level of that. So this will be the first energy level, that will be the second energy level. We have got p orbitals as well. So this is the s orbital here, this little block, that's an s orbital. That would be the p orbital. There are 3 of them. And we've got 3 blocks. Okay, so that's how we would represent the Aufbau diagram. Now, with this particular bond, what happens is there is an electronegativity between these atoms. So electronegativity is how much one atom is going to draw the bonded electron pair. They're quite greedy. Atoms that have got a high electronegativity really want a bonded electron pair. So with this ionic bond, what happens is the difference in electronegativity is really big. So this electron here that's sitting in the valence shell of sodium is going to be given to the chlorine atom. It's going to be given because that chlorine atom draws that electron so strongly that it actually moves over. And so it will then sit here. It will fill that space on the valence shell, in the valence shell. So we have a sodium plus ion, and we have a chloride minus ion, and then we have an electrostatic attraction between the 2. I just want to mention that these are called lone pairs of electrons, lone pairs. What does that mean? That means that they stand alone, they are very happy, they've got a partner, and so they're not going to be involved in in reaction, in bonding. This one, however, over here, that's on the sodium, and this one, this purple one that's sitting here on the chlorine, they are unpaired electrons, unpaired. And remember, the drive for these atoms is to become stable. When will they be stable? They'll be stable when they look like the electron structure of a noble gas. Remember the king, the noble gas. Right, so here's a brief description of it. Metal and non-metal, electronegativity difference of 2.1. The thing that's giving the electron becomes the cation, that's the positively charged. The thing that's accepting the electron becomes the anion. There's an electrostatic attraction, and what results is a big crystal lattice. Now this is sodium chloride over here. You can see here sodium chloride. And so they represent, so one of them will represent the sodium. I'm going to make it that one there, the sodium plus, and this one will represent the chloride ion. Okay, so there's that, the lines between them represent the electrostatic attraction, that force. In reality, we can't see that. But what we may be able to see is the actual crystals that form, these giant crystals that form, and they're absolutely beautiful if you are able to make them under correct conditions. So what about covalent bonding? Well, covalent bonding is about a non-metal and a non-metal. And we see that there is a slightly different interaction here. In fact, it's very different because there's no taking and accepting of electron. There is an overlapping of orbitals so that those electrons can be shared. There's an overlapping of the outer orbital. Those are the valence electrons, the valence orbitals. There is a sharing of electrons. Now, the electronegativity between the two is not as great as when ionic bonding is happening. So it is slightly less. However, if there is an atom that is quite strongly electronegative compared to the other, it is going to draw or pull those electron pair, the shared electrons. It's going to pull the electrons over to its side. Now we talk about an electron cloud because electrons can't really be pinpointed. They're moving so fast and they're so tiny. So we get like a scatter pattern, an idea of where they could be. So it forms like a cloud. And so we talk about the electron cloud. So the electron cloud is pulled towards the more electronegative atom. So if we have that situation, then we form polar molecules, and we'll get into that a little bit later. Non-polar molecules normally happen when we have atoms that are the same. So we have atoms that like being with one another. They are called diatomic molecules. And that would be something like hydrogen and hydrogen. Okay, hydrogen and hydrogen like being together. It forms diatomic hydrogen. Oxygen is another one, oxygen and oxygen, and we get diatomic oxygen. Okay, the result of this is called a molecule. So when we have got covalent bonding, it's called a molecule. Have a look at my picture. So if we see, this is an s orbital. You can see it's an s orbital. It's that spherical orbital. There are two of them. They're going to overlap, and you can see this overlap. I just want to change my pen color because you can't really see the blue. So you can see this overlap over here. So this is where the one atom would be, and that's where the other atom would be. So this is the overlap here. They get close enough so that they can overlap those orbitals that are on the outside, the valence orbitals, and then they're going to share those that extra electron. So there's a sharing of electrons. This is called a molecule. Right. How do we represent this in terms of the Lewis representation? Because having to draw this, these orbitals, is really tricky, especially when we get to p orbitals that overlap. It's very weird, and it takes a lot of time to draw those. So we have this Lewis representation to help us. Okay, so we've got hydrogen, and we have got chlorine. Okay. Now, we need to know what is in the valence shell. So let's go to the periodic table, and we see that hydrogen has an atomic number of 1, and chlorine has an atomic number of 17. Okay, so what does that mean? Well, hydrogen's only got one proton, means it's only got one electron. So we're going to place that on top over there. Now, Lewis representation is about how we represent the valence shell. So we have to know what it looks like. So for chlorine, I'm going to do this quickly. I'm going to do this SP notation. So in the first energy level, SP, 1s, that's going to have 2 electrons, right? Then we've got the second energy level, so it's going to be 2s, 2. Okay, maximum of 2. Then we've got the 2 p orbitals, and we've got 3 p orbitals, and each can take 2 electrons, so that's 6. Okay, so how many do I have now? 6, 7, 8, 9, 10. I've got 10. Okay, so let's keep going. So then I move to the third energy level, so 3s, 2. That's 10, 11, 12. And then 3p, what's left over? 17, right? So I've got to 12, so that's going to be 5. So they're going to be 5 there. Okay, so what is my outermost energy level here, or energy orbital? It is the third energy level. So it's 3s2, 3p5. I've got 7 electrons. Have a look here, 7 electrons in the valence shell. So that's how I'm going to do it, with dots. 1, 2, 3, 4, 5, 6, 7. Okay, now this hydrogen is going to overlap with this gap. You can see this gap over here. So how am I going to write it? I'm going to write it like this. H cross, there's my electron, dot, chlorine, dot, 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 dot. Can you see that? 1, 2, 3, 4, 5, 6, 7, and there's the overlap over there. You can see it's overlapping there. Right, let's have a look at water quickly. So water is H, and there are 2 of them, and so I'm going to put it like that, plus oxygen. What is the atomic number of oxygen? Let's have a look quickly. Oxygen is 8. Okay, 8. I've already looked at hydrogen. So what is going to happen here? I'm just going to quickly do my SP notation again. 1s2, 2s2, 2p. 1, 2, 3, 4. There are 8, so I must have another 4. So let's have a look at my external, my outer shell. My outer shell is going to be the second energy level, and so there are going to be 6 electrons in oxygen's outer orbital and its valency shell. So let's write those in. We've got 1 there for hydrogen, 1 there for hydrogen, and then for oxygen 1, 2, 3, 4, 5, 6. Remember, electrons will be on their own if they can. How are we going to write this? We're going to write this like this. We're going to have an oxygen, dot, 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 1 dot there, 1 dot there. I'm going to change the color of my pen and make that blue, and we're going to have hydrogen here and a cross, and hydrogen here and a cross. Those are the overlaps. Excellent. Grade 10s, try out chlorine on your own and see what you come up with. We're going to take a short break. When you come back, we're going to continue with metallic bonding.